Hi everyone, myself is Kantraj HD, Assistant Professor in Mathematics, Government First Grade College for Women, Kernagar. In this session, we are going to discuss on some theorems related to isomorphism of a vector spaces. Let's see. Let's see one theorem related to isomorphism. Under that first theorem is if F from U to V is an isomorphism, then F inverse from V to U is also an isomorphism. That means F is an isomorphism implies that its inverse also is an isomorphism. Let's see the proof of the theorem. Given F is an isomorphism, F is an isomorphism which implies that F is 1 1 and on 2. 1 1 and on 2, which implies that F inverse is also 1 1 and on 2. Since F is 1 1 and on 2, its inverse also both 1 1 and on 2. So only thing we need to verify whether it is a linear or not. So I consider let alpha comma beta belongs to U. Then I consider f of f inverse of alpha plus f inverse of beta, which is equals to, since what they given, f is a isomorphism, it means it is a linear, that means it is a homomorphism. Since it is a homomorphism, we can apply the rules for homomorphism. We get f of f inverse of alpha plus f of f inverse of beta. Since f is 1 1 and onto, that means it is a bijective. F into f inverse of alpha is equals to alpha plus, similarly f of f inverse of beta is equals to beta. So which implies that f inverse of alpha plus f inverse of beta is equals to f inverse of alpha plus beta. I take this as equation 1. That means this f taken to the right hand side. Similarly, or again, consider f of f inverse of c into alpha. F of f inverse into c into alpha, which is equals to, since f is a bijective, we can write this as c into alpha, which is equals to c into f of f inverse of alpha. F of f inverse of alpha, which is equals to f of c into f inverse of alpha, because f is a linear or it is a homomorphism, which implies that f inverse of c into alpha is equals to c into f inverse of alpha. I take this as equation 2. From 1 and 2, from 1 and 2, f is a homomorphism, which implies that f is an isomorphism, because already we know that f inverse is, from 1 and 2, f inverse is homomorphism, which implies that f inverse is an isomorphism, since f inverse is 1 1 and onto, and homomorphism, we say f inverse is also an isomorphism. This completes the theorem. Let's see one more theorem. Suppose that f is an isomorphism from a vector space. v2 u, then prove that the set v1 comma v2 comma v3 and so on vk a subset of v which is linearly dependent if and only if the set of images f of v1 comma f of v2 and so on f of vk are linearly dependent in u. That means if f is an isomorphism, then f is maps to a linearly dependent set to linearly dependent set of codomain. Let's see the proof of the theorem. So I consider let the set v1 comma v2 comma v3 and so on vk contained in v is linearly dependent, which implies that there exists a1 comma a2 comma and so on ak belongs to f with at least one of ai not equals to 0 by the definition of linear dependent such that a1 into v1 plus a2 into v2 and so on ak into vk is equals to 0. I take f on both sides, that is f of a1 comma v1 plus a2 comma v2 plus and so on ak comma vk is equals to f of 0 which implies that since f is a isomorphism, it is a linear or it is a homomorphism. Hence we can write the above equation as a1 into f of v1 plus a2 into f of v2 plus and so on ak into f of vk is equals to f of 0. f of 0 is a 0 element of codomain u, which implies that since ai not equals to 0 for some I less than or equals to k greater than or equals to 1, which implies that the set f of v1 comma f of v2 comma and so on f of vk contained in u is linearly dependent by the definition of the linear dependence. Conversely, we consider let the set f of v1 comma f of v2 comma and so on f of vk contained in u is linearly dependent, which implies that there exist c1 comma c2 comma c3 and so on ck belongs to capital F such that c1 into f of v1 plus c2 into f of v2 plus and so on ck into f of vk is equals to 0, which is equals to 0, or it is a 0 element of u. 0 as 0 element of u, I write it as 0 of u with ci not equals to 0 for at least for some I lies between k and 1. For some I lies between k and 1. Since f is a isomorphism, we can write f of c1 v1 plus c2 v2 plus and so on ck vk is equals to 0 of u. 0 of u, which implies that f of c1 plus v1 plus c2 v2 plus and so on ck vk is equals to 0 of u, which implies that c1 v1 plus c2 v2 plus and so on ck vk belongs to kernel f, belongs to kernel f because its image is a zero element of codomain, hence it is an element of kernel f. Since f is a homomorphism, it is 1 1. Since it is 1 1, kernel of a homomorphism is singleton 0. Therefore, we can write c1 v1 plus c2 v2 plus and so on ck into vk is equals to 0 element of v. 0 element of v. Since ci not equals to 0 for some I, for some I where I lies between k and 1, which implies that a set v1 comma v2 comma and so on vk is linearly dependent in v. This completes the theorem. Let's see the one more theorem on isomorphism. That is, suppose u and v are finite dimensional vector space, or then u and r are isomorphic if and only if they are the same dimension. Let's see the proof of the theorem. I consider a proof. Let u and v are isomorphic. We need to prove that they are of the same dimension. They are of the same dimension. Let f is an isomorphism from u into capital V. U into capital V, and u is of the dimension n, which is a finite value. Then the basis of u is, I take u1 comma u2 comma and so on un. This is the basis of our domain u. Consider the set f of u1 comma f of u2 comma and so on f of un, which is contained in V. Suppose c1 comma c2 comma and so on cn belongs to R, such that c1 into f of u1 plus c2 into f of u2 plus and so on cn into f of un is equals to 0 element of V. 0 element of V, which implies that f of c1 into u1 plus c2 into u2 and so on, cn into un is equals to v of 0 because f is a isomorphism, nothing but it is a homomorphism. Since it is a homomorphism, we can write this, which implies that c1 comma u1, sorry, c1 into u1 plus c2 into u2 plus and so on, cn into un belongs to kernel f, belongs to kernel f because their image is a zero element. But since f is a isomorphism, it is 1 1, therefore the kernel value is always a singleton 0, which implies that c1 into u1 plus c2 into u2 plus and so on, cn into un is equals to 0, that is 0 element of domain 0u, which implies that c1 is equals to c2 is equals to and so on, cn, all the scalars are equals to 0 because the set u1, u2 and so on, un is linearly independent. Thus, because they are the basis, since they are the basis, they are linearly independent, which implies that f of u1 comma f of u2 comma and so on, f of un is also a linearly independent, is also a linearly independent. Again, let v belongs to capital V is an arbitrary element, is an arbitrary element. Since f is an isomorphism, f is an isomorphism, which implies that there exists small u belongs to capital U such that v is equals to f of u. v is equals to f of u. But u is equals to a1 into u1 plus a2 into u2 and so on, an into un because u1, u2 and un are the basis of capital U. Therefore, f of u is equals to f of a1 into u1 plus a2 into u2 plus and so on, an into un, which is nothing but v is equals to a1 into f of u1 plus a2 into f of u2 plus and so on, an into f of un, which implies that set f of un comma f of u2 comma and so on, f of un spans capital V, spans capital V because here we take V as a arbitrary element that is expressed as a linear combination of f of u1, f of u2 and f of un. Since every element of V are the linear combination of f of u1, f of u2 and f of and so on, f of un, they spans the complete space f of complete space V, which implies that u and capital V are of same dimension, are of same dimension. Conversely, let capital U and capital V are of the same dimension. What we need to prove? U and capital V are isomorphic. U and capital V are isomorphic. So let U1 comma U2 comma and so on UN and V1 comma V2 comma and so on Vn are the basis of capital U and capital V respectively. Capital U and capital V respectively. Then define a map G from U to V by G of U1, G of A1 into U1 plus A2 into U2 plus and so on AN into UN is equals to A1 into V1 plus A2 into V2 plus and so on AN into Vn, where AI belongs to capital F. Let's suppose G of A1 U1 plus A2 U2 and so on AN UN is equals to G of B1 into U1 plus B2 into U2 and so on Bn into Un. That means the images of two vectors are equals, I consider, which implies that G of A1 U1 plus A2 U2 plus and so on AN UN whose image is A1 V1 plus A2 V2 and so on plus AN Vn, which is equals to, similarly RHS image is B1 V1 plus B2 V2 plus and so on Bn Vn. Take all the terms of RHS to LHS. I have A1 minus B1 into V1 plus A2 minus B2 into V2 and so on AN minus Bn into Vn is equals to 0 of V. 0 of V, which implies that AI minus Bi is equals to 0 for all I. For all I, since a set V1 comma V2 comma and so on Vn is linearly independent. Vn is linearly independent, which implies that AI is equals to Bi for all I. AI is equals to Bi for all I, which implies that G is a 1-1 mapping. G is a 1-1 mapping. Since AI is equal to Bi, we have A1 into U1 plus A2 into U2 plus and so on AN into UN is equals to B1 into U1 plus B2 into U2 plus and so on Bn into Un we get, hence it is 1-1. Let V belongs to capital V, which implies that there exists D1, D2, and so on. Dn belongs to F implies that V is equals to D1 V1 plus D2 V2 plus and so on Dn Vn, because V1 V2 and so on Vn are the basis of the capital V, which implies that there exists an element in capital U such that d1 of v1 plus d1 into v1 plus d2 into v2 plus and so on dn into vn, which is equals to g of d1 into u1 plus d2 into u2 plus and so on dn into un, because g is defined like that, which implies that G is onto mapping. G is onto mapping. And since G is a linear mapping, since G is a linear mapping, which implies that G is an isomorphism. G is an isomorphism, which implies that U and V are isomorphic. U and V are isomorphic. This completes the theorem.